So Onur is one of Yale's students. Once a student, always a student. He's the Strecker Endowed Chair at Carnegie-Mellon University.
Okay, thank you, Derek. It's a great pleasure to be here talking at Yale's 35th birthday, even though for some reason it's called 75. I'll talk about rethinking the systems we design. This is the agenda I have for the talk. I'll talk about some principles that Yale has taught and how we violate those principles today in systems design, talk about some solution approaches, and conclude. But first, let's start with the real reason we're here today, and it's Yale's 35th birthday. This is what he used to look like when he was 25. Actually, to be more accurate, it's 27. This is from HPCA 2006, when he organized the conference, and he actually, I believe he was the first person who have armadillo races in a conference. Those armadillos were quite good. So I'll start with some teachings of Yale Patt. I think first and foremost, Yale is a teacher. And I wanted to get some slides from his course, which are actually available these days, and they haven't changed a bit from spring 2002 when I actually took this course, except they're in PowerPoint form now. And this is one of the slides. It is the design principles. It's actually he uses it in his first lecture, and I'll actually elaborate on these a little bit. Basically, 3 design principles he puts up for systems: critical path design, bread and butter design, and balanced design. And these are the slides that I took the liberty to expand for my own lecture notes. Basically, bread and butter design means that spend time and resources on where it actually matters. Optimize for the common case. Don't make the uncommon case terrible. Balanced design, well, it's balanced, system balance. Design to eliminate bottlenecks. Critical path design, find the maximum speed path. Or I will rephrase this on my own. Basically, accelerate the critical thing that is actually important for you. So my takeaways out of these, they're quite reasonable principles. They're actually stated by other principled thinkers in similar or other ways, and one of them is here, Mike Flynn. The Flynn's bottleneck, many of us are aware of. Endowed, actually, his principled thinking actually led to a lot of other kinds of designs. Butler-Lampson's hints for computer system design. So I will take the liberty to generalize some of these principles in the rest of the talk. The problem is, I believe the systems, the platforms we design today violate these principles grossly. Some systems components individually may not violate them, or might not seem to violate them, but the overall system itself doesn't spend time or resources where it matters, at least much of the time. It's grossly imbalanced, and it doesn't optimize for the critical work, critical application that we're executing, or critical thing, critical path. And I'll give you some examples of this and talk about some solution approaches in the next, I guess, 30 minutes. One thing Yale taught me, that you can have a single slide and talk about it for hours and hours. I cannot do that very well. I can have 100 slides and talk about it, hopefully in 30 minutes. We'll see. So a computing system really consists of 3 key components: computation, communication, storage, and memory. And I believe the 2 are actually similar and becoming more similar, memory and storage. And these are the units. If you look at today's system, they're overwhelmingly processor-centric. Processor is heavily optimized and it's considered the master. This was actually in a couple of other talks earlier today, Trevor's talk being one of them, Bill Daly's being another of them. Many system-level trade-offs are constrained or dictated by the processor, and all data is actually processed in the processor. If you look at the data storage units, they're dumb slaves, and they're largely unoptimized, except for some that are on the processor die. Yet, this is an anonymous quote from a DEC employee. I believe I've heard many names for that DEC employee from different people. It's really the memory that's limiting our performance today. This is data from my thesis. I'm happy to present again at UT Austin, where I got my PhD. But if you look at much of the time, the processor is stalling waiting for the misses, even in an optimized memory hierarchy. So the memory system is the major bottleneck that we have today in terms of performance, energy, quality of service, reliability in many workloads. And it's becoming increasingly so due to many trends. I'll go through this relatively quickly. We have increasing hunger for more data and its fast analysis. We want to pack and consolidate more on chip for efficiency purposes. memory bandwidth and capacity are not scaling as fast, and we want to guarantee SLAs, quality of service, service level agreements, and user satisfaction. And at the same time, DRAM technology is not really scaling well to smaller feature sizes, exacerbating all of these bottlenecks: energy, reliability, capacity, and bandwidth. So this processor memory disparity, in my opinion, leads to designs that do not spend time or resource where it matters, violates the bread and butter design, that are grossly imbalanced while it's a balanced design, and does not optimize for the critical work or application. As a result, the processor becomes overly complex and bloated. Even if you do in-order processors, the chip itself becomes overly complex and bloated to tolerate all of these memory-related issues. And complex hierarchies are built just to move and store data within the processor. So when you look at a processor today, this is my cartoonish view, exacerbated. The red parts are doing computation, and the rest is moving data and storing data. And even within the red parts, you have register files and L1 caches that move and store data. So the forgotten memory system becomes dumb and inadequate in many aspects. So I'll give you some examples. If you're not convinced out of this, I'll give you some examples and let you decide on your own. Let's take a look at one example operation that's a primitive in many applications today: bulk data copy and initialization. This is true for many bulk operations that we do today. If you want to copy one page to another page in memory today, this is what happens. The processor brings the source page byte by byte all the way into the L1 cache and writes it to the destination page byte by byte, and then the destination page needs to be written back to memory byte by byte. Eventually, you perform the copy. This is high latency. It has high bandwidth utilization in a critical system bottleneck. This causes cache pollution unless you do it through the DMA, so you can eliminate that. And this leads to unwanted data movement. All you're doing is copying one page to another page. Maybe you're not even touching that page later. As a result, if you want to do this at a 4 kilobyte copy via DMA, this is the, you can do it at 1,046 nanoseconds and 3.6 microjoules. So a better system design, in my opinion, going forward is to do this. The processor tells the memory, copy this page to the destination for me. And the memory does that. This is low latency, low bandwidth utilization, no cache pollution, but you could have eliminated that, and no unwanted data movement. So you can actually have a mechanism that reduces at 1,046 nanoseconds to 90 nanoseconds, and that reduces at 3.6 microjoules to 0.04 microjoules. And the mechanism is really simple. If you know how DRAM operates at the subarray level, at the very low level, basically it operates at the bulk level. If you want to read those 8 red bits out of DRAM, 1 byte basically, you need to activate the entire row, which brings the data into the row buffer, and then issue a read command. Instead, row clone, one of the ideas one of my students developed, Vivek Seshadri, does this. Basically, if you want to copy this page to another page in DRAM, you first activate row A, bring the data into a row buffer, and then in the next step, you basically activate the destination row, which basically takes the data into the row buffer and drives it into the cells of the destination row. Of course, you need to deactivate this row implicitly. This basically achieves a copy within 90 nanoseconds, 2 consecutive activates, without going off chip at all, without even going off the subarray. So you need, of course, mechanisms to do this movement more generally within the DRAM chip. If you add all of those, it's very, very, very little area cost in DRAM. And the latency and energy savings are significant. Basically, you can reduce latency by almost 12x, reduce energy by 74x, if the destination and source are in the same subarray. You get different benefits depending on your destination and source. So that calls for a system design that can take advantage of this. So how do you take advantage of this? If you have this kind of simple mechanism in memory, basically you need to have an end-to-end system design to take advantage of this. The software needs to communicate the occurrences of these bulk operations to hardware. You need to somehow ensure data coherence. You need to maximize latency and energy savings, and you need to handle data reuse. And I'm not going to talk about that, but these are, I believe, important resource direction going forward. But the benefits that you can gain are potentially significant. These are some applications which do a lot of bulk copying and bulk initialization, and it can actually get significant performance and energy reductions. And the reductions are even more in multi-core systems where you're running these applications potentially in a consolidated way with other applications that are just accessing the memory bus, not doing bulk operations. So going forward, maybe we should be thinking about the memory system as a more active agent in the system that we're designing, maybe as a peer to the processor. Because we have all these processors, if you will, accelerators, that are operating on things that are efficient, that are good to have, but they don't have access to this huge data store that many applications today need to have access to and operate on. So why don't we think of memory as maybe a conventional accelerator, or maybe a conventional processor, but perhaps add specialized capability in it such that we don't actually try to do something that's not good for the technology that we build memories with. So one thing that we're looking into is how do you actually enable ultra-efficient search in memory. Memory stores some database, and processor actually sends queries into this database, and memory itself does that search. Let's say you search a hash of an image in this memory with the structures that are similar to a row clone, except they do some kind of computation or filtering, and memory returns the results, filtered results back, and then the processor maybe focuses on those results more. This is much more of a peer-to-peer system, and maybe at some point we can think of models where memory can launch computations on the processor for data that requires more processing. There are many questions related to this. I'm not going to go over these. What is the right partitioning of computation capability? What is the right low-cost memory substrate? What memory technologies are best enablers? I do not believe DRAM is the best technology for this. And once you do this, how do you actually rethink and ease some of the algorithms and applications today that try to avoid some of these operations? For example, when we actually looked at row clone, a lot of applications try to avoid those copies like the plague. Except there may be some cases where those copies are useful when you're programming applications, especially when you're doing non-volatile memory programming, for example. Okay, I'll go into 2 more examples very quickly until Derek kicks me out of here. But the second example, because of the processor-centric design, I think we've ignored some of the things that are happening in memory. And one is DRAM refresh. If you look at DRAM today, it's kind of a bad memory because you need to refresh it, right? Because its capacitor charge leaks over time. And the memory controller needs to refresh each row periodically to restore its charge. This means that you need to refresh each row every 64 milliseconds. If you look at Matteo's Mare Nostrum supercomputer, it has 100 terabytes of memory. It's almost 2 to the 50 bytes. Basically, a row is 2 to the 13 bytes. So you're refreshing about 2 to the 40 rows every 64 milliseconds. That's 1 tera rows. That's a lot of waste in terms of energy. Performance degradation, when you're refreshing, you cannot access memory, or at least parts of memory. You get quality of service impact, and a refresh rate actually limits DRAM capacity scaling. I'll go through these relatively quickly. This is device capacity, chip capacity, DRAM chip capacity on the x-axis. This is percentage of time device spends refreshing. This is the throughput loss, if you will, of the device. Today it's at 8%. If we keep the scaling trend of DRAM, it'll be 50% at 64 gigabit chips, almost 50%. And this is the percentage of DRAM energy spent refreshing. Today it's about 15%. Going forward, at 64 gigabits, it'll be around 50%. And you can argue with the numbers, and I will argue with these numbers myself, even though they're my own and my own students' numbers, but the trends are exponential. The trends remain the same. So how do we actually fix the problem? I think I'll give you one potential idea. Just by examining the system, we can do much better. If you look at the retention time profile of DRAM, you don't really need to refresh everything every 64 milliseconds, because the retention time profile looks like this because of process variation. Basically, there are very few DRAM cells or DRAM rows that need to be refreshed every 64 milliseconds. Most of DRAM you can get away without refreshing for 256 milliseconds. If you just identify these different rows and different retention times of them, you can basically design a system that doesn't refresh these rows every 64 milliseconds. That way you can reduce the refresh rate by almost 75% right off the bat. The key question is how to do this. I'm not going to go through this in detail. Basically, we proposed one mechanism in ISCA 2012 that basically profiles retention time of all rows, which is actually the hardest step over here, and stores the rows into bins by retention time in the memory controller. And the memory controller basically changes the refresh rate depending on which row it's trying to refresh at that point in time. And you can get significant performance benefits as well as energy improvements by reducing the refreshes by almost 75%. The key question is actually how to do this. You can say that, oh, this is the problem of DRAM manufacturers. Let the DRAM manufacturers deal with it. Unfortunately, that's not the case, because it's very difficult for DRAM manufacturers today to profile the retention time of all rows. What happens is you can determine the retention time of all rows as a DRAM manufacturer, but once you solder the DRAM chip on the board or on a DIMM, you expose it to high temperatures, which change the retention time profile completely. So it's really a system-level problem that needs to deal with this. So let me give you one more example. There are actually many, many examples in memory, but I'll talk about one more example in reliability. DRAM scaling problem is real. I think we've been hitting the memory scaling problems a lot earlier than processor scaling problems. Basically, what is DRAM scaling? We want to reduce the size of the circuit to increase its capacity and density. The problem is the capacitor and the access transistor must be large enough for reliable sensing, low leakage, and high retention time. And now that we're at about 24 to 20 nanometers, we're actually seeing issues. It's become a real problem that the system should be concerned about and maybe embrace. And I'll give you one example. This happens in real DRAM chips today. You can buy DRAM chips off the market that were manufactured between 2012 and 2013. And you can, I cannot guarantee you that, but it's very likely that you'll see this problem. If you do this to the chip, if you activate one row, deactivate it, and you keep doing that over and over and over and over, within a refresh interval, enough times you'll get errors in the neighboring cells. This happens because of cell-to-cell interference that the DRAM manufacturers were not able to contain, and as a result it escaped into the field, and we've shown that in Yoongu Kim's ISCA paper this year. Basically, we've tested chips from 3 different manufacturers. You can guess who they are. Most of the chips that were manufactured, more than 80%, actually exhibited these errors. And the ones that were manufactured in 2012 and 2013, actually all of them exhibit these errors. You can actually download this program from our website. You can test it on your DRAM chips in your computer. Basically, if you write a program like this, what it does is it exercises these 2 rows repeatedly over and over. I guess my computer cannot exercise as fast as I can. But as a result, you can get errors in the neighboring rows. And these are actually real CPUs. And these are some example numbers. You can perhaps demonstrate these errors on your own by downloading the program. The problem is basically this is a serious reliability issue. And maybe even more seriously, it's a security issue. Because if someone actually does this, if someone actually sneaks this program into a cloud computing provider, basically a totally different virtual machine in the cloud may be affected. And you can get silent data corruption because of these errors. Okay, so how do you solve the problem? I'll just give one potential solution direction, and then I'll hopefully try to wrap up time. Basically, we can try to tolerate it. We can make DRAM and controllers more intelligent, and I believe this is a good solution direction, just like flash memory and disks. And people are actually trying to offload a lot of computation to the controllers that we have on disks and flash memory today. We can eliminate or minimize it, replace DRAM with, or more likely augment it with a different technology, or we can embrace it. I believe we should pursue all of these solutions, and maybe you can plug your own solution in the ... over there. One example I believe that's interesting is exploiting memory error tolerance. These are some applications. Applications inherently have different error tolerances at their different regions, and error tolerance is different across applications as well. Basically, if you can identify vulnerable data and tolerant data, you can design a memory system that has reliable memory versus low-cost memory, and as a result, you can have heterogeneous reliability and you can exploit it. And we've done this study on Microsoft Web Search application. If you can actually do this, you can still get a very high availability that's actually within what Microsoft wants for their data centers, while reducing server hardware cost by 4.7%, and while potentially scaling memory much better. Anyway, I'm not going to talk about the several other things. I'd be happy to talk about them later. But let me try to go back and talk about some solution approaches and some directions for the future. Basically, we need to rethink the entire memory storage system given the trends that we're facing today, to satisfy data-intensive workloads, fix many issues we're having with DRAM, enable emerging technologies. And this enables a better overall system design going forward. To do this, I believe we need to find a better balance between moving data versus moving computation. Even for a bulk copy and bulk initialization, we shouldn't be moving all of that data all the way into the processor. And we need to enable system-level memory and storage quality of service to provide predictable performance. There were a couple of other talks that talked about this, to build more controllable and robust systems. Very briefly, some solution principles based on what I've discussed so far. I believe we need to look at more data-centric system designs instead of computation-centric system designs. Instead of centering everything around the computation units, perhaps we should be centering things around the memory. To do this, we need better cooperation across the layers of the system. Yale calls this breaking the layers, and I'll have a picture of its transformation hierarchy that I cannot avoid in a talk. Wenmei couldn't avoid it either. But basically, we need to carefully co-design the components and layers, system, architecture, and device, have more flexible interface. The interface we have to memory is terrible today. And this is Yale's transformation hierarchy. We need to break the layers across here, as well as within the components that we have in the system. Even here, we have very, very rigid layers. Even within the chip, if you go to a company, they do not necessarily talk with each other across the different parts of the chip. Well, we need to do better than worst case design. This is very well known, I think, in the CPU world, but not in the memory and storage world. If you look at refresh, it's really designed for the worst case. And several others talk about heterogeneity or specialization and asymmetry in design. This definitely enables a more efficient design since there is no one-size-fits-all. So let me draw some concluding remarks. I'm not terribly over time, I believe. But I'll take some more slides from Yale's 382N course. Basically, he defines the role of the architect as this. You need to look backward, examine old systems, look forward, listen to the dreamers, and I believe that dreamers, those dreamers are really important. And I agree with Wenmei when he talked about the HPS papers' fate, or likely fate today in today's conferences. I believe today's conferences are terrible at listening to the dreamers. They don't want dreamers, they want really data crunchers, if you will. We need to look up, we need to examine the nature of the problems, and we need to look down, predict the future of the technology. I'll have one more quote from another famous architect. Maybe some of you can guess who this is. Basically, we need to design architectures based upon principles and not upon precedent. I believe the architectures that we have been designed based upon precedent, the precedent of centering everything around computation. And this quote is actually from a different architect. It's from Frank Lloyd Wright. And if he had, I believe, thought about precedent, he would have designed something like this instead of this, which is falling water, I guess, which is one redeeming factor of being in Pittsburgh. Okay, let me give you final concluding remarks. I believe it's time to design systems to be more balanced, more memory-centric. It's time to make memory and storage a priority in system design rather than a second thought, and optimize it and integrate it much better into the system. It's time to design systems to be more focused on critical pieces of work. And I believe a lot of the critical pieces of work, again, are bottlenecked in memory. So this is my bold claim. Future systems will or should be data-centric and memory-centric with appropriate attention to principles. And I guess I did add a couple more slides from Yale's lecture notes, because I believe these are new. These I hadn't seen before. So there's something that's changing based on the principles. This is Yale slides. Yale says, people are always telling you think outside the box. And Yale says he prefers expand the box. So I think if you think of what I said, I'm not saying something really radical in one sense. I'm just saying expand the box to memory. Thank you.